Welcome everybody to the first episode of the X plus Y Factor. My name is Paul Levy. I'm the Director of Undergraduate Admissions in Maths and Stats at Lancaster. And I've got with me today Jonny Evans, Dr Jonny Evans, who is a lecturer in the department. One of the things that we'll be talking about today is a first year course that he teaches called Linear Algebra, and which he has just taught. And it was a very eventful period of time, obviously for lots of reasons. So we'll come back to that a bit later. So first of all, Jonny, can you just say a bit about who you are, how long you've worked at Lancaster and so on, and where you've worked before that?
Yeah, sure. So thank you, Paul. It's a pleasure to be here. So I came to Lancaster about a year ago. So before that, I was in London at UCL for about 7 years. And then before that, I was in Switzerland at ETH. And then before that, in Cambridge. So it's finally ended up in Lancaster, which is a great place to be. Yeah.
So both you and I have lived in Switzerland and then moved to Lancaster, which is close to the Lake District. So I don't know if
general love of nature and hills and
exactly.
things.
Yeah, I lived in Lausanne for a few years. So I was at the other École Polytechnique in Switzerland. So your research specialism is sort of broadly speaking in algebra, yeah.
No, it's in geometry.
Geometry, yeah. We have a group which is algebra and geometry. Yeah. I would consider it algebraic, but perhaps you consider it more geometric.
Indeed, yeah. So I definitely find myself more on the geometric end of the spectrum, but it's kind of symplectic geometry, algebraic geometry, that kind of thing. So there is some algebra in there, yeah, definitely.
Okay. Right, I said I would say we would discuss a little bit about Math 105, which is linear algebra. So that's the first year sort of introductory linear algebra course that we have, which is taken by both the math students and some of the minor students who are just doing 1/3 of maths in their first year. So it's the second time you've taught it, is that right?
Yes, indeed. I taught it just after I arrived last year. It was quite a baptism of fire. So
okay, well, you had a second baptism of fire, didn't you? Because
yeah, I did.
What was the time frame for that? The introduction of the lockdown and so on, and you having to quite rapidly change your teaching.
Yeah, so the teaching started end of May, and of course lockdown was sort of end of March. So I was already starting to think maybe it was going to have to be that way. But yeah, I started recording videos towards the end of March and then over Easter. And yes, and then we had a fully fledged online course by April to be delivered. Yeah, it was good. It was good fun. I've had some experience with this lecture flipping before, where you record the videos and then you do something else with the lecture time. I did a course like that about topology in the past, and I actually quite like it because it removes a lot of the pressure to get through the material as fast as you can in the lectures, and it allows you to interact more with students. Obviously, it's a bit different when it's online because you can't interact in quite the same way. But I found, so we had live sessions online, like we're doing now, basically using Teams, and they work pretty well. So the students do a lot of interaction through the chat facility. They ask a lot of questions, or you can do things like asking them multiple choice questions or true false questions and getting them to vote on the answers very easily and online, obviously. And they seem to engage pretty well with that. So yeah, it's not as it doesn't feel like you're sitting talking at a blank screen, and hopefully for them it doesn't feel like they're just getting information. Is the sort of interaction going on. So yeah, I enjoyed it actually.
Okay, so the usual format would be you'd have 4 lectures a week, and it would be in a large lecture theatre, and there's a limited amount of interaction because I've also taught one of these first year courses where in the lectures, because there are so many people there isn't that much interaction. So the kind of obvious first thing to think about when you were moving to online, because we had to move online in that period, the university was closed and all workplaces were most workplaces were closing. The first thing to move is the lectures. Now I'm going to put a link in the description box below to your YouTube channel, which did you set it up just for this course this year?
No, it's got
Did your
the
people-
videos from a previous course that I taught, like, well, not like this, but a flipped course on topology and some other random videos. But yeah, probably about half the videos are from this linear algebra course.
Right. Okay. So anybody that's interested can go and have a look at how those online lectures worked, and you've cut them into bite-sized chunks because people don't tend to sit and watch a 1-hour video when they're watching something online. And then in terms of the actual interaction with the students, in a normal year, we would have workshops, which would be much smaller groups, maybe 15 or 30 students, and the teachers go around and talk to the students and ask them, have you got any problems with this problem? How are you getting on? They give them feedback on their homework and so on. And that's the thing that you've replaced with this sort of online
live sessions, yeah.
Live session, a bit like this. Yeah, yes, I sat in on one of those, and I think I sat in on one of the first ones. So the students at that time, it was very novel,
yeah,
and they were quite interested in the novelty of it.
Yes, I'm not sure that. I think that may have worn off by the end, but certainly some of them were still very engaged. Yeah.
Yeah. Okay. So so that's a sort of trying to adapt to the situation as best as we could at that period. This is first year module, so those students have to sort of pass the year for progression, and I think that the progression this year is going to be quite loose requirements for students anyway because of the exceptional circumstances. Now next year, I'm sure if there's anybody watching who's an applicant or a potential applicant, they'll be wondering what on earth are we going to do next year, and I think we're still not 100% sure, are we?
No, indeed. I mean, my guess would be that we will prepare as if the worst case scenario happens and everything's sort of off campus. But obviously the preference is that we are on campus. And so I'm teaching another course next year, fourth year course on Lie groups and Lie algebras. So my plan for that is to do the same, record all the lectures, and then if we're physically there on campus, I'll teach it as a flipped course where we use the lecture time to talk to one another and do problems together and that kind of thing. And if we're online rather than on campus, then I'll just do it the same way I've done this and run the live sessions online. Yeah.
Okay. So
let's wait to see what happens.
So flipped is the terminology for when you do that, you just do the lectures online, and then the situation where you have more interaction is that's what you're focusing on with the teaching. Is that right?
Yes, exactly. Yeah. So flipped learning is something that education theorists have been trying to get us to do for many years. So maybe they're kind of, they're thinking, great, everyone's taking it up now by necessity. And I do think it's good because it means that lecture time that would ordinarily just be me proving a theorem or giving a definition or something, they've already seen the definition beforehand, they've watched the videos in theory, and you're using that time to talk to them and interact with them and check that they've understood what's going on, or they can ask you questions, and it's a lot more like school, I guess, more interactive.
Yeah, but I mean, to give an idea of the time frame, we've got a meeting tomorrow in the department, don't we, where we're going to talk about our teaching plans for next.
Indeed.
Yeah.
Yes.
So, but in a week's time, I may well be talking to somebody else and have a clearer idea of how we're going to teach. But the problem is, we need to plan for all eventualities. So I think in an ideal world, in an ideal world, we would be using some components of this sort of blended learning model, but we would be able to pick and choose according to what we decided was best. And we're not really in a situation of being able to choose what we think is best. It's what we're going to have to do out of necessity. So it's not a particularly sort of clear situation. So that's to sort of express the doubts, but also that there's a lot of planning going into that sort of teaching for next year, isn't there?
Yeah.
That's kind of socially distant teaching. Now, I asked you to pick out a problem, and so I thought we could take an interlude now for you to explain your problem. Sure. Just for a few minutes, and then we'll chat about it. Now,
okay, yeah. So what I'll do then is I'll share my screen so I can write and stuff, and then you maybe be able to see what's going on. Hang on, so I'm going to share my screen. Okay, can you see that? should say rational approximations. You see that?
Yes.
Yes.
Yeah.
Okay. Cool. Okay. So this is about it's a problem about rational approximations. So we know maybe that this number 22/7 is quite a good rational approximation for the number pi, which is of course an irrational number, and it comes out to about 3.1429 something, maybe 8. And in fact, it's the best approximation you can get amongst fractions where the denominator is 7. If you try any other number with a denominator 7, you're not going to get as close as this one. In fact, better still, it's the best approximation you can get with fractions where the denominator is at 7 or less. So you can't do better if your denominator is 3, 4, 5. And as we allow bigger and bigger denominators, we still don't do better than this for quite a long time. So, you know, if you allow 11 in the denominator, then like 35/11 is quite close. It's like 3.1818 ... But that's still not as good as this. If you allow 15 in the denominator, like 47/15 is about 3.13 recurring, and that's still not as good as this. So it's not until you get to 355/113 that you get a better approximation. At that point, it gets very, very good. So it's 3.14. I'm going to have to look at this. 1415929 ... So that's pretty close to what pi is. I can't remember what pi is, but you can look it up on your calculator if you have one. And as you allow bigger and bigger denominators, you keep finding fractions that do better than any fraction before them, like this 22/7, or like this 355/113. And, you know, as you keep going, you'll get a sequence of better and better fractions. And these are called the best rational approximations. So they're quite difficult to compute for pi, because pi is a bit of a mysterious number. So I want to ask a question about an easier number, which is the golden ratio. So the golden ratio is 1 plus √5/2, which is what, again, I'm going to have to look this up. So 1.6180339887, blah 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 blah. Okay, so you can calculate this on your calculator using, you know, square roots and whatnot. So the question is, can you find the first few best rational approximations of the golden number? So just, you know, using calculator or computer maybe, try different denominators in increasing order and see, you know, how good an approximation you can get for those increasing denominators. And then look at the numbers you get, and you should see a pattern. So observe this pattern. Can you explain this pattern that you observe? So somehow the question don't quite make sense until you've started actually doing the calculations, but you will observe a pattern, I think. And so the question is, why is that pattern there? Why do you observe that pattern? Okay, does that make sense?
Okay, thank you. Yeah. So just because we have a range of different people watching, so the point here is that that both pi and this 1 plus √5/2 are irrational numbers, so they're not equal to fractions. And yes. So another way of saying that is that the decimal expansion doesn't repeat.
Indeed.
It's not a repeating decimal expansion. So if you look at these 35/11 and 47/15, they have repeating decimal expansions, but that's not true for pi of this 1 plus √5/2. So the best you can do is approximate by these fractions. And then how do you approximate as best as possible? So we'll maybe come back to that at the end of today's show, but otherwise. And
if you're getting bored during the show, you can always start thinking about it now and doing calculations.
You certainly can, or you can press pause. But and then I'll try and think about a way to come back to sort of discuss a solution to this problem next week when we'll have somebody else on the show. Okay, thanks for that. Now,
should I stop sharing that now, or
if you like? Yeah. Great. Okay, so your research area, as you said, is symplectic geometry. So you describe it as in geometry. And we had a bit of a chat before we started this, and you're the kind of ilk of mathematician that finds it quite difficult to explain to sort of ordinary members of the public what your research field is about. And I'm a bit like that as well. So maybe just sort of say a little bit about the kind of development of the subject of mathematics through the degree, and kind of what kind of stages you're looking at, and where, you know, the maths that you would learn during your degree, kind of how that relates to what you might do in the research area that you study.
Sure. So my particular interest in this comes from trying to understand things like high dimensional spaces, things you can't really visualize very easily, which is why when you were asking me before, do you have any good pictures that illustrate your research? It's like, not really. The pictures tend to be pretty poor, but they're very good at approximating things in high dimensions. So I'm really interested in trying to draw pictures that approximate high dimensional spaces. So for example, maybe you've got a 4-dimensional space you want to understand, but maybe you can encode it completely in a 2-dimensional picture. So the picture doesn't look very interesting, but it turns out to encode a lot of information. Or maybe you have a 6-dimensional space you want to understand, and you end up drawing a 3-dimensional picture of that. So, you know, really to actually make sense of these pictures, the kind of things you're going to need are differential geometry. So it's the kind of stuff that you start learning maybe in first year with vector calculus. So I think the course Math 115 at Lancaster introduces this. And I think for the people doing theoretical physics, they take something else which is equivalent that also covers the same sort of materials. So differentiating vector functions and that kind of stuff, grad, div, and curl. That's the kind of first inkling maybe you get into this. And then, so after that, I'm trying to think where the next point. There's a geometry of curves and surfaces course in third year, right? Which will be the next sort of step towards this, trying to understand, you know, 2-dimensional spaces, but more abstractly than the way you'd ordinarily think about them, where you're trying to actually compute things about a curved surface in 3 dimensions. And then in the fourth year, there's this module, Lie groups and Lie algebras, that I mentioned I'm going to be teaching next year. So that's probably as close as you get to the sorts of things I think about. So that's studying spaces which are also what's known as groups. So they're some sets of symmetries of other objects. But at that point, maybe it gets a bit hard to explain unless you've already done the first 3 years.
Well, I think one of the things that you mentioned the word space several times there, didn't you? So that's a sort of recurring theme through a lot of mathematics. Is different notions of what a space is, and you might want your space to be something like a model of physical space, such as the space of the, you know, of ordinary the space around us, and then that might have certain properties of sort of continuity or, you know, smoothness of the space. But then in other contexts, you want some of the other notions to apply. So that's space and geometry. That's the kind of the intuition for a lot of the things that we think about in geometry. And when you refer to higher dimensional spaces, you're really talking about a notion of dimension, which is a measure of the number of different directions you can go in a space.
So for example, if you think, maybe I can share my screen again, then I can draw something. Can you see that now?
Yeah.
Again, yeah. So here's a space. Is the sphere. And I'm going to call this the 2-dimensional sphere. A lot of people think this should be a 3-dimensional sphere because it's in 3 dimensions. But actually, the surface of the sphere is only 2-dimensional, right? Because you only need 2 coordinates, like you say, 2 directions to parameterize the points on the sphere. You need the longitude and the latitude. That's it.
Yeah.
So if you think about the surface of the sphere, that's 2-dimensional. So what would be an example of a 4-dimensional space? It would be something like you have a point on the sphere and then another point on the sphere. Right, so if you have 2 points on the sphere, you need to know the longitude and latitude of both of those points, and that's 4 coordinates. So to parameterize pairs of points on the sphere, you need 4 numbers. So that's an example of a 4-dimensional space. And the kinds of pictures I was talking about, the kind of slightly cartoonish pictures of spaces that I tend to draw, you draw the sphere as an interval like this, just a line, straight line. And the way you reconstruct the sphere from that is you stick a circle over every point in the line, except the endpoints where you stick a single point. So then it kind of reconstructs a sphere like this. And the picture I would draw of the 4-dimensional space where it's pairs of points on the sphere would then be a square. Because you have then, you know, that's the vertical direction is one of your spheres and the horizontal direction is the other sphere. So this is a picture of a particular 4-dimensional space.
Right.
If you want a 6-dimensional space, you could do this. and draw a cube.
Yes.
That's a very specific one, but you know,
So,
you can do much more interesting ones.
What's your history? Where did you study? How did you get into, decide that you wanted to be a mathematician?
I didn't. Originally, I wanted to be a physicist. I was very interested in physics. And so I read this book, I think it's a book by Kip Thorne about black holes and time warps and stuff. And he said, in the US, if you want to be a physicist, you do a degree in physics and then you become a physicist. In the UK, if you want to be a physicist, you go to Cambridge and you do maths and then you become a physicist. So I was like, okay, let's try that. And then it didn't work because I went to Cambridge, did maths, and then became a mathematician because it was much more interesting. So, yeah.
I mean, all kinds of things about string theory and so on probably related to that bit of advice.
Yeah,
I think.
absolutely.
But,
definitely. A lot of the things I do are motivated by ideas that came originally from string theorists. Yeah.
Right. Okay. So there's been a lot, sort of very sort of fertile kind of sort of ideas transferring between physics and mathematics. I think some would argue that mathematics has benefited more from that interchange than physics has. But that's.
I think that's probably true,
some of the physics blogs and so on. But okay. So I think we're going to sort of wrap up now. I don't know if there's anything else that you wanted to say. I don't think we need a hint for the problem. It's fairly clear. You just need to sort of go. I think
it's giving a hint would maybe
ruin it. Yeah.
Take away from the exploration aspect of the beginning of it. I'd have to kind of tell you what the rational approximations were. But what I was planning to do was actually make a YouTube video around this, maybe exploring this. So maybe if you keep looking at my YouTube channel in a week's time or so, there'll be a video that explores this problem a bit more. So
okay, well once that's there, we can update the notes down below, and people can go and find the solution to that problem.
Cool. Yeah.
Okay, well, thank you very much. I mean, obviously, I'll be in a meeting with you tomorrow, but we're talking about teaching for next year. But thanks very much for introducing that, and good luck with everything. Okay.
Yeah, you too. See you later. Thank you for that.